Hi, everyone. My name is Sumir Kataria, and I'm an engineer on the Android team. I work on architecture components, and today I want to talk to you about a new library we have called WorkManager and background processing in general on Android. So let's talk about background processing in 2018. What are we trying to do these days? Just this morning, I was trying to send a picture of my lovely wife and my beautiful son to the rest of my family. So that's an example of background processing. We're also sending logs, syncing data, processing that data. All of this work is being done in the background. And on Android, there's a lot of different ways you can do this work. Here's a lot of them. You can do things on threads and executors using Job Scheduler, Alarm Manager, async tasks, etc. Which one should you use, and when should you use it? Meanwhile, Android also has a lot of battery optimizations that we've introduced over the last few years. For example, we introduced Doze Mode in Marshmallow. If you've been following Android P, we've had app standby buckets. In Oreo, we restricted background services. So all of these things have to be taken care of as a developer. And finally, we always have to worry about backwards compatibility. So if you want to reach 90% of Android devices, you want to at least have a min SDK of KitKat. So given all of this, what tools do you use and when do you use them? And the trick behind this is that you have to look at the types of background work that you're doing. I like to split this up into two axes. The vertical axis here is the timing of the work. Does the work need to be done right when it's specified, or can it wait for a little bit so that if your device enters Doze mode, you can still do it after that? Also, on the horizontal axis here, how important is the work? Does the work only need to be done while your app's in the foreground, or does it absolutely need to be done at some point? So for example, if you're taking a bitmap and you decide that you want to extract a color from it and update your UI with it, that's an example of foreground-only work. You don't care about it once the user hits home or back. That work is irrelevant. Meanwhile, if you're sending logs, you always want that to happen. That's an example of guaranteed execution. So for things that are best effort, you really want to use things like thread pools, RxJava, or coroutines. For things that require exact timing and guaranteed execution, you want to use a foreground service. So an example of this would be that the user hits a button and you want to process a transaction and update the UI and the state of the app based on that. That really needs a foreground service. That needs to happen right then. Your app cannot be killed by the system while that's happening. This fourth category is very interesting. So you want guaranteed execution, but you're OK if it happens later. Doze mode can kick in. And there's a variety of ways to solve it. On your APIs, you'll use Job Scheduler. If you want to go a little further back, you can use Firebase Job Dispatcher to do that. And if you don't have Google Play services, you'll probably end up using Alarm Manager and broadcast receivers. And if you want to target all of those things, well, you'll use some mix of these four things. And that's a lot of APIs, a lot of work to be done. WorkManager falls here. It's guaranteed execution that's deferrable. So WorkManager, let's talk a little bit about its features. I just mentioned guaranteed execution is also constraint aware. So if I want to upload that photo that I talked about, I only want to do it when I have a network. That's the constraint. It's also respectful of the system background restrictions. So if your app is in Doze mode, it won't execute. It won't wake up your phone just to do this work. It's backwards compatible with or without Google Play services. The API is queryable, so if you have enqueued some work, you can actually check what is its state. Is it running right now? Has it succeeded or failed? These are things that you can find out with WorkManager. It's also chainable, so you can create graphs of work. So you can have work A depending on work B and C, which in turn depends on work D. Also, WorkManager is opportunistic. So this means that we will try to execute that work in your process as soon as the constraints are met, without actually needing Job Scheduler to intervene or call you out and wake you up. It doesn't wait for Job Scheduler to batch your work if your process is up and running already. So let's talk about a little bit of the basics and talk through the code. So I just described the example. I want to upload that photo. So how would I do that using WorkManager? Let's talk about the core classes. There's the worker class. This is the class that does the work. This is where you will write most of your business logic. And there's a work request class, which comes in two flavors: one-time work request for things that just need to be done once, and periodic work request for recurring work. And these will both take a worker. I'll show you just now. So here's my upload photo worker. It extends the worker class, and it overrides the do work method. This is the method that will run in the background. We'll take care of that on the background thread. You don't need to put it in the background thread. So you simply do your work. So in this case, we upload the photo synchronously, and we return a result. So in this case, let's say we succeeded. And the worker result enum here has three values: success and failure, which are fairly obvious, and retry, which says, I encountered a transient error. Let's say that the device lost network connection in the middle. So retry me after a little bit with some backoff. So now that I have this, I can create a one-time work request using the upload photo worker, and then I can enqueue it using WorkManager.getInstance enqueue. So soon after this is enqueued, it'll start running. You'll upload your photo. But I just talked about this. What if you lose connectivity in the middle of this? Or even before this, what if you never had connectivity? You actually want to use constraints in this case. So an example of the constraint here you want to use is you make a constraints builder, and you say, set required network type to be connected. So you need a connected network connection. You build it, and you also set the constraints on the request that you just built. So by simply doing this and then enqueuing it, you make sure that this work only runs when your network is connected. So let's say we want to observe this work now that we've done it. So I want to show a spinner while this work is executing, and then I want to hide the spinner when it's done. How would I do that? So as I said, I'll enqueue this request. And then I can say get status by ID on WorkManager using the request ID. So each request has an ID. And this returns a live data of the work status. If you guys remember architecture components, live data is a lifecycle aware observable. So now you can just hook into that observable, and you can say, when that work is finished, hide that progress bar. So what is this work status object that you were looking at the live data? It has an ID. This is the same ID as a request. And it has a state. The state is the current state of execution. There's 6 values here: enqueued, running, succeeded or failed, blocked, and canceled. And we'll talk about the last 2 later. So let's move a step up in concept here. Let's talk about chaining work. So I promised that you can actually make directed acyclic graphs of work. How would you do that? Let's say this is my problem now. I'm uploading a video. It's a huge video. I want to compress it first, then upload it. So these are both eligible for background work because they're time-intensive things. So let's say I have 2 workers, compress photo worker and upload photo worker. They're both defined to do the things that I just said. So you can make work requests from them, and you can say WorkManager begin with compress work, then upload work, and enqueue it. So this ensures that compress work executes first, and once it's successful, then upload work goes. And if you were to write this out, because that was a very fluent way of writing it, what happens behind the scenes here is that begin with returns a work continuation. And a work continuation has a method called then that also returns a work continuation, a different one. So you're using that to create that fluent API. So you can actually use these work continuations and pass them around if you want, etc. So let's say that I'm uploading multiple photos. I take lots of photos. No one takes only just one photo of their child. So how would I upload all of these in parallel? Well, so let's say I've got a work request for all of them. I can literally just say .enqueue and put all of them there. It's a var args, so you can pass more than one thing there. And these are all eligible for running in parallel. They may not actually run in parallel depending on your device and the executor being used and all of that, but they could be. So let's choose an even more complex example. Now you want to filter your photos, so you want to apply some kind of, I don't know, grayscale filter or sepia filter to them. Then you want to compress them. Then you want to upload them. How would you do this? WorkManager makes it very simple. So first you say, begin with, you do all the filter works in parallel. After those have all completed successfully, then you do your compression work. And after those have completed, that is completed successfully, then you do your upload work. And don't forget to enqueue at the end. So we've talked about all of that, but there's a key concept that I want to cover that's very much related to chaining. This is inputs and outputs. So let's talk about this problem that I have here. It's a MapReduce, and it's really a good way of explaining a MapReduce is to give an example. I love reading. I've loved reading Sherlock Holmes novels since I was a kid. And the other day I was thinking, well, Arthur Conan Doyle has a very specific way of writing. What are the top 10 words he uses in his books? Well, how would I figure that out? I would go through each book, and I would count the occurrence of each word, and then I would combine all of that data and sort it so that I would find the top 10 of those. This is a distributed problem that we could call a MapReduce. And for inputs and outputs, the common unit of operation here is a data. The data is a simple class that's a key value map under the hood. The keys are strings, the values are primitives and strings, and the array versions of each. So this is kind of like a bundle or a parcelable, but it's its own thing. It's serializable by WorkManager, and we limit it to 10 kilobytes in size, and I'll go more into that part later. So how do we create a data? So in Kotlin, you can make a map very easily. So in this case, we're mapping the key file name to the value a steady in scarlet.txt. That's the novel that I'm going to look at. And I'll convert it to a work data. So this is a data object. And once I create my work request builder, I can set the input data on it. So this is the input data of that map. And I pass it along. So inside my worker, I can actually retrieve this input data by just calling the getInputData method. And from that, I can get the string for the file name. So now I have the file name. And I can say, count all the word occurrences in this file name. That's some method that I've written somewhere else. And I can return my success. But you don't want to do just that. You actually want to also have outputs, right? Now you've done all this work. It should do something. There should be an output for it. So let's say that method that we have returns a map of words to their occurrences. We can convert that map to a work data. And we can call a method called setOutputData that sets this data. So getInputData, setOutputData. So the key observation that you need to know here is that the worker's outputs become the inputs for its children. So what happens is the find top 10 words worker, which goes next, its input data is coming from the previous worker. So in this case, you can pass the data all the way through, find the top 10 words, and return out. So the data flow for one book becomes like this. I'll count all the word occurrences in that book. I'll pass it to the find top 10 words worker. Its input data will be whatever I pass through, and it'll do the sorting or whatever it needs to do. But here's a really tricky thing. What happens when you have multiple books? What's the input for the find top 10 words worker? You're passing multiple pieces of data, but I've only been able to get one input data. What happens to the rest of them, or how do they combine? For this, you want to look at input mergers. So input merger is a class that combines data from multiple sources into one data object. And we provide two implementations out of the box: overriding input merger, which is the default, and array creating input merger. You can also create your own, but let's talk about these two. First, overriding input merger. So we have two data objects here, each with their own keys and values. What does overriding input merger do? It first takes the first piece of data, and it just puts everything in a new data object. So it's an exact copy of this. Then it takes a second piece of data, and it copies it over. So overwriting anything that's the same key. So in this case, the name Alice becomes Bob, and the age of 30 becomes 3 days. Note that it changed type, so a number became a string here. The scores key was new, so it just got added. Note that if we did this in reverse, instead of Bob, you would have Alice as the final output. So this is something a little tricky. You want to make sure that overriding input merger is the right tool for the job, but it is very simple. What about array creating input merger? This is the one that actually takes care of those collision case. So in this case, let's go just key by key. The name becomes an array of Alice and Bob. Color becomes a singleton array of blue because it's only defined in one of them. Scores, notice that there's one integer and one array of integers. These combine and they just concatenate together. Order is not specified, but all the values come through. What happens for age? So there's an integer and there's a string. This is an exception. We do expect it to be the same basic value type. So let's go back to that example I was telling you about Sherlock Holmes. Implicitly, there's an input merger before the stage. So we combine all of that data. And which input merger do we want to use? So we don't want to throw away any of this calculation that we've done. So we actually want to use an array creating input merger, which preserves all of the data and gets it through. So how do we do that? Well, we just say set input merger on the request builder of the find top 10 words. So it merges data using an array creating input merger. So you say begin with the count words workers, then do the find top 10 words worker, and then in queue. So for example, if the first book had 10 instances of the word Sherlock, 5 of Watson and 30 of elementary, and the second one had 12, 15, and 5, you would get arrays like this. Sherlock would be 10, 12, Watson would be 5, 15, elementary would be 35. So in your find top 10 words worker, you would sum all of that up, sort them, find the top 10, and that's your output. And I just said that's your output, right? So you can actually observe the output in your work status using that live data. So you can actually get that output data. So that's super useful because you can display it in your UI. How do you cancel work? So I just decided to send up a picture, but I'm like, wait a sec, this is not the picture I meant to send up. How do you cancel that upload? Very simple, you just say cancel work by ID. But do note that cancellation is best effort. So the work may have already finished. These are all asynchronous things. They may be happening in the background before you've had a chance to do that cancel work. It may already be running or finished. So it's best effort. OK, so let's talk a little bit more about tags. And tags are solving this problem. IDs that I just told you about are auto-generated. They're not human readable. So they're actually UUIDs under the hood. And you can't really understand them. They're not useful for debugging. If you log them, they're not going to make sense. What kind of work was running? I don't know. It's just some big number. I don't know what that is. Tags solve this issue. Tags are a readable way to identify your work. So tags are developer-specified strings by you, and each work request can have 0 or more tags. You can query and cancel work by tag. Let's look at an example. So I used to work on the G+ team here, and the G+ app supports multi-login. So you can have multiple users logged in at the same time. And each of those users could be doing several kinds of background work. You could be getting favorites. You could be getting preferences. So if you have 3 users logged in on your phone, and they're doing 2 kinds of work, you have 6 things happening. How do you identify what you're looking at any given time? Well, you can use tags. So for example, in this work request builder, you can add tags to say, this is user 1, and this is the get favorites operation. So now you can actually identify that work. And if you wanted to look at the statuses, you could say, give me all of the work for user 1. And this will return a list of work statuses as a live data. Because each tag can correspond to more than one work request. So this is a list of work statuses. Similarly, you can also cancel all work by tag. Cancellation is best effort again. But you can cancel all of one particular kind of work in this case. Tags are also useful for a couple of other reasons. Tags namespace your type of work, as I just told you. Like, you can have tags for the kinds of operations you're doing, get favorites, get preferences, etc. But they also namespace libraries and modules. So if you're a library owner or a module owner, you should always tag your work so you can get it later. Let's say that you have a library and you move to a new version of that library in your app. Maybe you want to cancel all the work you had. You can cancel all work by your tag. So always use tags when you are using a library. And work status also has tags available in it. So if you're ever looking at a work status, you can get the tags for that work and see what you yourself called it in the past when you enqueued it. One more thing I wanted to talk about is unique work. So unique work solves a few different problems. But one of the common ones that almost every app has is syncing. You want to sync when you first launch the app. You want to sync maybe every 12 to 24 hours to get the freshest data. And you may also want to sync when your language changes. Maybe you have a version of your data in a different language. So you want to sync at that point too. So you're doing all this syncing, but you really only want one sync active at a time. You don't want 4 sync operations running. Which one's the right one? Which one wins? You don't know. You just want one. Unique work can solve this. So it is a chain of work can be given a unique name. You can enqueue, query, and cancel using that name, and there can only be one chain of work with that name. Let's take a look at that sync example. So if I say begin unique work with my name, let's say sync in this case, and that next argument is what I call the existing work policy. So if there is work with this name, sync, what should I do with it? In this case, I say, keep it. I want to keep the existing work, ignore what I'm doing right now. The next argument is actually your work request, in this case, a sync request, and you enqueue it. So if there's work with the name sync already in flight, it will keep that. If there isn't, it will enqueue this and execute it. So this is how you dedupe your syncs. So here at Google, we love chat apps, and maybe you're updating your chat status. So you want to say, I'm bored, and then 10 seconds later, I'm watching TV. Then I'm bored again. OK, I'm going to sleep. And you're in a bad network connection state. You have bad Wi-Fi, and maybe the first thing hasn't gone through when you type your second chat status update. And really, the second one should win, and the third one should win over that. So you want to make sure that the last one wins. How would you solve this? Here's a simple function. You don't even need to read the rest of it. It's the last line that I want you to care about, which is begin unique work. Your name is update status, and you choose the replace option. Replace cancels and deletes any existing in-flight operations of that name. So the last one always does win. In this case, if you have 2 update chat status calls, the last one will win. And finally, I love music. I love the Foo Fighters. I was building a playlist the other day with all their songs. There's a lot of songs. There's like 150 or 200 songs. And I was doing all of this. I was adding a song. I was shuffling 2 songs around. I was moving something to the bottom of the list. I was deleting a song because I had it already somewhere else. These are all things that I want to do using WorkManager, but how would I do that? These things all have to execute in order. And so since the order is important, we provide the ability to use the append existing work policy that says, do this work at the end of the list of update playlist operations. So just append this to the end of this thing. So everything else must successfully execute before this executes. So you can add operations to the end. So existing work policy, as a summary, there's 3 types: keep, replace, and append. A few notes about periodic work. It works very similarly to everything you've seen so far. Just a couple notes on it. So the minimum period length is the same as Job Scheduler. It is 15 minutes. It is still subject to DOS mode and OS background restrictions, just like any of the other work we've talked about. It can't be chained, and it can't have initial delays. And we think that that just sort of makes good API sense. It's much more reasonable to think of it in those terms. All right, so we've talked a lot about code. Let's talk about how it all works under the hood. So you've got a work. You enqueue it. We store it in our database. What happens after that? Well, if the work is eligible for execution, we just send it to the executor right away. By the way, this executor, you can actually specify it, but we do provide one that's default. But let's say that your process gets killed. Well, what happens then? How does it get woken up, and how does this work run again? So if you're on API 23+, we send it to Job Scheduler as well. And Job Scheduler invokes an IPC, wakes up your process. It goes to the same executor, and that's where it runs. If it's an older device, and you use Firebase Job Dispatcher and use our optional dependency, we can send it to Firebase Job Dispatcher. Same thing, invokes an IPC, runs it on that executor. What if you don't have that, or you're not using a Google Play Services device, so you're using something else? We have a custom alarm manager and broadcast receiver implementation. And the same thing, uses an IPC, wakes up your app when the time is right, and runs the job. A couple implementation details. So Job Scheduler and Firebase Job Dispatcher through Google Play Services, they provide central load balancing mechanism for execution. So if every app on your device is trying to run jobs, they'll load balance them. They'll make sure that you're not running too much work on your device and burning up your battery. The Alarm Manager implementation that we have, unfortunately, can't do that because it's only aware of your own app. Of course, newer concepts like content URI triggers, idle, doze mode, et cetera, are only available at the API levels that they were introduced at. So those methods will be marked with requires API with the appropriate API level. We take care of obtaining wake locks when necessary. So especially this is true for the Alarm Manager implementation. Don't take wake locks in your workers. You don't need to do that. We take care of it for you. Finally, let's talk a little bit about testing. You want to test this app. We provide a testing library. It has a synchronous executor. Use WorkManager as normal to enqueue your requests. And we provide a class called test driver, which executes enqueued work that has constraints. So we can just pretend that the constraint's been met. Periodic and initial delay triggers are coming soon. We don't have them yet. So if you wanted to look at the code for it, you can initialize the test WorkManager. You can get the test driver, create and enqueue your work as you normally would with a constraint in this case. And we can tell the test driver, hey, all constraints are met for this work. Your work executes at that point synchronously, and you can verify the state of your app and make sure that everything's right. I also want to talk a little bit about best practices before I end here. It's very important to know when to use WorkManager. WorkManager is for tasks that can survive process death. It can even wake up your app and your app's process to do the work. So for example, it's OK when you want to use it to upload media to a server. It's also OK when you want to parse data and store it in your database. It's not OK for that example I gave earlier. You're extracting the palette color from an image and updating an image view with it, because that's foreground-only work. It's also not OK when you're parsing data and just updating the contents of a view, because you could switch screens, you could go in the background. It's not work that needs to use WorkManager. It doesn't need to survive process death. Also, it's not OK to process payment transactions in it if they care about timing right then. So if you click Buy and you want to update the state of the app, that really needs something else. So that last one needs a foreground service. The other two may just use thread pools or RX. Also, WorkManager is not your data store. Instances of data are limited to 10 kilobytes each when serialized. So data is really meant for light intermediate transportation of information. You can put file URIs or keys to other databases in there if you want. You can put simple information to update your UI. If you want to use a full data store, I would recommend using Room. Yeet would be very happy that I'm saying this. It's an awesome database. Finally, be opportunistic with your work. So here's a filter compress upload example again. The reason that these are not just one big job is because they all have different constraints. So they can execute at different times. Let's say I'm getting on an airplane and I'm uploading a bunch of images and running this chain of work. Well, I go into airplane mode. Maybe I don't have network for the next 12 hours because I'm flying across the world. Well, the other work can still execute, and it should. So if you architect like this, you can do that. This also, by the way, makes your code a little bit more testable, because you can write a test for filtering that isn't conflated with compression and upload. All right, and I want to talk about a few next steps for you. If you need to reach us and talk to us about WorkManager, we are in the Android sandbox, just behind us, I think, over here. d.android.com/arch/work. That's more information on the official developer website about WorkManager. These are all the Gradle dependencies. The first one's a required one. The second one is if you use Firebase Job Dispatcher, also include that. There's a testing library, and of course, we have Kotlin extensions as well. WorkManager is part of the architecture components in Android Jetpack. And we have a bunch of talks here. Tomorrow, navigation controller, 8:30 a.m. Hope you guys make it there. And thanks for being part of this talk. We look forward to hearing back from you soon. Thank you.